All right, guys, so section 2.1 today, starting in with quadratic functions and models. Again, I just got through saying it, but 2-day section come in here. We've got a few goals. Scroll up a little bit so we can see them. The first goal, we want to be able to put a quadratic equation into vertex form. I would say that, yes, we have the other two goals, and they are important, but really, that first one, that's going to be kind of the indicator of success. If you leave section 2.1 knowing how to get into vertex form, you're doing good things. Okay. Second goal, we want to be able to identify the vertex, axis of symmetry, and the x-intercepts of a quadratic function. Basically, now we're talking about the graph. If we look at a graph, do we know what the heck we're looking at, basically, is what we're talking about. And then number three, just to sort of go one step further, we want to be able to identify the minimum and the maximum values of any quadratic. The good news is that we already know exactly how to do that. If I have a parabola looking something like this, would we agree that the vertex is just the minimum point? Okay, and if I had another one, okay, now it's pointing downward. Now the vertex is what? It's a maximum point. Okay, so we know how to do that. It's just, again, classifying these vertices as minimum or maximum values. Okay? All right, so starting with the definition, again, we have a definition for a quadratic function. Again, I know that we had this, this exact little equation up on the board a few minutes back. Again, if we were to let a, b, and c be real numbers where a is not equal to 0, quadratic function, again, we're thinking a, x squared plus b, x plus c. Again, a is always the coefficient in front of the x squared, b is the coefficient in front of the x, while c is the constant. Typically, what are you looking for in order to where you could look at something and say, yep, that's quadratic. What's the giveaway? X squared. Again, that's your highest degree. Again, we don't have x to the third power because that would make it a cubic function. Again, if x squared is the highest degree, then yes, you are looking at a quadratic function. So a couple of other pieces here that we've already talked about, actually. The graph of a quadratic function is a parabola. We know quite a bit about parabolas. Again, I would highly encourage you to just always keep in the back of your mind what the parent function of the quadratic function is going to look like. All parabolas are going to be symmetric with respect to what we call the axis of symmetry. Sometimes that's shortened to just being called the axis. And again, this is another situation that we do not want you to overthink it. If we have a parabola, it's going to have a vertex, like you said. There is a vertical line that goes through the vertex. That's what we refer to as the axis of symmetry. Okay, vertical line, again, goes through the vertex. Okay. So again, thinking about what it means to be symmetric, if we were to fold over that line, the left side of the parabola is going to map exactly onto the right side of the parabola. Okay? I've already used this term probably 50 times today, but the point where the axis intersects the parabola, again, that minimum point or that maximum point is referred to as the vertex. Okay? Pretty important. It's like the most important point, I mean, considering we're going to be striving to get into what we call vertex form. We want to be able to find that vertex. If you know where the vertex is, you know what your parabola, where your parabola goes and what it looks like. Okay, any questions so far? All right, just quick review of transformations. Again, hopefully this takes like 30 seconds. If we have x squared plus c, what are we doing? I'm going up c. What about x squared minus c? Now I'm going to go down c. What about x plus c quantity squared? That's going to be going to the left c. What about x minus c squared? That's going to be to the right, c. What about negative x squared with the negative on the outside? Okay, so again, reflect. Use that x-axis. Okay. I think the calibration is a little off. What about negative x quantity squared? That's going to reflect on the y-axis technically, but, and I say technically because what's going to happen, excuse me, what's going to happen with a quadratic? Thinking about your parent function. Because it's an even function, are we going to be able to tell a difference if we have a negative there? Again, I'm not saying that it isn't reflecting on the axis of symmetry, but we can't tell. Again, because of the axis of symmetry and how it works. What about c out front as a coefficient? C times the quantity x squared. If c is greater than 1, what's that? Vertical stretch. Then what if c is less than 1? I should say less than 1 but greater than 0. Then that's going to be vertical stretch. Okay? So hopefully we're feeling pretty confident with those transformations. Again, we talked about them in chapter 1, but again, they don't go away. It's not like, all right, that was how we graphed in chapter 1. Now let's graph a different way in chapter 2. That doesn't happen. We've got our standard set of rules. All right, so standard form of a quadratic function. This is one of the spots that has, frankly, caused some frustration over the years. I think, again, I'm pretty sure that you're all aware of this. I didn't write our textbook. Again, I'm not a textbook author, but I obviously use our textbook quite a bit. I am assuming that they had a typo in the textbook. Somebody should have been proofreading this stuff, okay? They're referring, again, so I pulled this directly out of our textbook. In section 2.1, which is where we are right now, I feel like they kind of go back and forth with calling the same thing standard form and vertex form. And back and forth and back and forth, okay? So here, they're saying standard form of a quadratic function. Guys, this is vertex form, okay? This is what we're talking about. You might remember 2 slides back, they called that standard form, the ax squared plus bx plus c. That's standard form. This is what we call vertex form, because if we know what we're looking for, we can reach right in there and say, yep, there's h, there's k, so that's my vertex. Okay, so please don't confuse the two, but I know that, I'm pretty sure that they screw it up even in their directions a couple of times. You're going to be able to catch it, because it's like they give it to you in standard form, and the directions say, put this in standard form. They mean vertex form, okay? They mean vertex form. So, what we're getting at here, again, we have f of x is equal to a times the quantity x minus h squared plus k. We always have to throw in that little cover your backside that, you know what, a cannot equal 0. Kind of skipped over it previously when we talked about standard form 2 slides back, but why is it that a cannot equal 0? Yeah, it's going to multiply by x and it goes to 0, and you won't be able to tell if x is squared or cubed or to the 94th power. It's not going to matter if it's equal to 0, right? So in order to actually be, to be able to square that variable, thus making this quadratic, we can have anything other than 0 in place for that constant a. All right? So we've got a lot going on within that one little equation. Like I said, though, it typically breaks down to those 3 variables, a, h, and k. Okay, just again, not that it's the same thing, but let's think back to slope-intercept form. We've used that so often over the years that basically, if you think about y equals mx plus b, there it boils down to m and b. If you know m and b, you're in business. You could write the equation, solve the equation, draw the graph of the equation. You can do all of those things so long as you know m and b. Here, there's just now a 3rd variable. We have a, h, and k. hk is going to tell you where the vertex is. A is going to tell you which direction. If it's positive, just like your parent function, it opens up. If it's negative, again, we're flipping over the x-axis, so we're pointing downward. Again, same deal. If a is greater than 0, less than or greater than 1, less than 1. Again, we're thinking about vertically stretching, shrinking, stuff like that. Okay. Again, one of the keys there is that again, we don't want to think too hard about it. If a is positive, we're opening upward. Negative, it's opening downward. So if we're looking at this example, f of x, it's equal to 2 times the quantity x minus 4 squared minus 7. So before we start to unveil where the vertex, axis, and direction that we're opening, let's first identify a, h, and k. What are you going to tell me a is equivalent to here, please? A is 2. That's positive, so which direction are we going to be opening? Just like your parent function, it's going to be opening upward. Okay? Now, does everybody understand the connection I'm trying to get you to make mentally here? I keep saying just like your parent function. Parent function being that f of x is equal to x squared. Isn't that technically 1x squared? So it's positive. You've got a positive value up front. Our picture, our graph is going to follow suit here. Okay? Again, we have a positive lead coefficient. We're opening upward. If it's negative, that's when we reflect it and we're opening downward. Okay, what about h? H is going to be 4. Remember, it's the amount that's being subtracted from x. What about k? Negative 7. Very good. So if h is 4 and k is -7, then now we know that our vertex is at 4, -7. So if I were to start plotting some points here, 4, 3, 4, 5, 6, 7. We said that we're opening upward. Gosh, I'm glad you're paying attention. That makes one of us. It is down 7. Thank you. I didn't know that I had more in my graph. 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6, 7. And if I drew this parabola just like that, is that parabola perfect? Okay. What would make this more precise? Yeah, but which 2 points would make this to where we're like, now we got it? The zeros. If we could determine exactly where we're crossing the x-axis in those 2 locations, then we would say, yep, that's a perfect graph now. And I'm not saying does it look pretty? You know, that's not what we're getting at. It's, do we have the points in the right location? Okay. So for right now on this particular problem, we weren't asked to find the zeros, and it didn't say to actually draw a perfect graph or anything like that. But got a pretty good idea, I suppose, as far as what we're looking at. Okay, the last thing that we're supposed to identify is the axis of symmetry, which again is going to be that vertical line that goes through my vertex. So where is that axis located, please? Okay, so close. I agree with that, with what you said. I agree with the 4, but we need to make an equation out of this. It's going to be x equals 4, again, because it's that vertical line. Right? Now, what tends to happen, and again, I'm not accusing you of doing this, but what often happens is that students will look at it and say, I know it's 4, but I can't remember if it's x equals or y equals. So I'm just going to write 4 and hope that he's in a good mood as he's grading this stuff. As you got to understand that when we talk about the axis of symmetry, it's not a good mood, bad mood thing. It's an equation. It's if you just say 4, that can mean a lot of different things. As soon as you say x equals 4, I can't argue with you. It's a vertical, it's a vertical line that you're plotting on that graph. All right, guys, what questions can I answer about this first slide? Is a lot of this stuff coming back to us? How many of us remember vertex form from last year? Remember working with that a little bit? Okay. All right. So I threw a slide in here on your notes, and I know that it's probably really difficult to read, but this is just another step-by-step. Every step is shown. Here's how you do completing the square. Okay. So again, I feel like we've worked through like 4 or 5 examples already today. Are we good with just saying reference this slide of your notes if you need it? Okay. All right. So, guys, I've gone back and forth on this the last couple of years as far as do I even show this? Because what tends to happen is that people will read the title here and say completing the square shortcut. Great. I don't like completing the square. I'm going to use this shortcut. And it works. Again, please don't get me wrong. That's, again, ultimately the reason why I do tend to show this is that it's an option. And again, I'm a firm believer. I've talked about it already quite a bit this year, that it's my job not to necessarily tell you that this is the way you have to do things. It's my job more realistically to show you that these are all the options as far as how you could do these things. This is an option. I don't like it because 99% of the students who try to use it mess it up, but this is an option. You would, again, the reason why it gets messed up is that there's a lot of variables and it's straight memorization. It works, absolutely works, but if you're looking for identifying H or K and you don't want to go through the whole process of completing the square, you could get there this way. This is basically still you're doing the completing the square, but in a very, very modified version to where you kind of like skip all the work and you jump straight to the end, which is why we call it a shortcut. And this is how everything would shake out. Like I said, it works, absolutely works. But memorizing and getting it perfect over the years, a lot of people have gone with this method, and unfortunately, if you make one mistake, like if you add here instead, you're literally going to get every single problem wrong. Okay, that's going to put your vertex in the wrong location. I mean, and then at that point, there's not a lot I can do for you. So again, I feel like all that I'm doing is persuading you not to use this. That's not really what I'm trying to do, but